Now we've been using the periodic table to build up electron configurations, but the first periodic table was invented long before the electron was discovered, and certainly long before anyone thought of quantum numbers, which we now use to explain the shape of the periodic table. It was the first version was published by Dmitry Mendeleev, a Russian chemist, in about 1869. Now, he was a solitaire player, and he was looking for patterns in the behavior of elements. So he wrote the elements down on a series of cards, and he tried to deal them out like you would in playing a solitaire game until he could see some patterns. Here's a card for hydrogen and a card for lithium. Now, they have something in common. If you look at their oxide formulas, hydrogen combines with oxygen and it forms water. Lithium combines with oxygen and it forms lithium oxide. Now notice that both of those formulas kind of look the same. You got two of the element with an oxygen. Now, other elements don't do that. If you look at beryllium and magnesium, their oxides look like this. If you look at aluminum, its oxide looks like this. If you look at another element, indium, its oxide looks like this. Now he did what I'm doing here. He arranged the cards so that everything with the same oxide formula or the same general formula for chemical compounds. He also looked at hydrogen compounds that some of these elements could form. If they had similar formulas for their oxides or their hydrides, he would put them in the same column. And he decided then that he was going to do even better than that, not just arrange them in columns, in families, he called them, or groups. He was going to arrange them across so that they were increasing in mass as you went across. And when he did that, you get a table that looks something like this. He didn't know about helium, but I'm going to put it in anyway. This is the lightest element. That's the next heaviest element. And then you get lithium, and he puts it under there because they have the same oxide formula. Then beryllium, which is a different one, but it's the next one up in mass. And then you have boron, carbon, nitrogen, oxygen, fluorine, and neon. And when you look at those, you see that everything in the same column has got the same oxide formula, and you've got them increasing in mass as you go across. Now, we know that the right way to set up the table now is not to make things increase in mass across a row, but to make them increase in atomic number. And you can deal out another row of cards, like this. And another row. And then we kind of skip across here. And there were some elements that he's going to fit in here. I'm not going to write them all. But there was an element, zinc, there. And there's an element, germanium, which clearly fit here. All of these things form oxides that look like this. CO2, SiO2, GeO2. So germanium, Ge, clearly belongs in that column. Zinc belongs in this column before this column. And it would mess up the, there was no element between zinc and germanium that was known. And it would mess that pattern up if he put germanium over here. So he skipped a space and put this over here. He said, there's a missing element in there. He said, I don't know what this element is. You're going to discover it someday. But if I look at the other cards that are around this, when I deal them out, I can predict some things about this missing element. I'm going to call it Eka aluminum. And he even gave it a symbol, Ea. And he said, this unknown element is going to have physical properties that are sort of the average of the surrounding elements. For example, if you want to predict the atomic mass of this element, you're going to average the masses for aluminum and indium, and zinc and germanium. So if you average those four masses, you're going to get an estimate of what the atomic mass here is going to be. I'm actually asking you to do that in the question underneath. And he said, you can do this for other physical properties too. Take density. If you want to predict the density of Eka aluminum, this unknown element, average the densities for its neighbors. And it should have something pretty close to that density. So I'm also asking you to do that in the question below. If you want to predict the oxide that this element will form, well, it'll form the same oxide as the other elements in the column. Now, boron forms an oxide that looks like this. Aluminum forms an oxide that looks like this. Indium forms an oxide that looks like this. So you can see everything that he put in this column forms an oxide that has 2 atoms of the element and 3 oxygens combined with it. So this should be the same thing. So you could predict the properties of missing elements here, which was incredibly powerful. And it was quite a coup when just a few years later, in the 1870s, they discovered this element. They called it gallium. Gallium Ga. And it had almost exactly the properties that he predicted for it. So when you're looking at chemical properties, these elements have got chemical properties that are similar to everything in their own column. And they've got physical properties that are kind of the average of all the surrounding elements. Let me write that down. I'm going to say roughly chemical properties are similar to other elements in the same column. Now, the same column is sometimes called the group. So a thing will chemically resemble things that are in the same group. And in fact, these chemical properties vary in a very regular way. If you look at the first column on the periodic table, and you look at these elements in that column, all of them are soft silvery metals. They're so soft you can cut them with a butter knife. And all of them will react pretty violently with water when you throw them into water. The reactivity, though, is not the same for all of these elements. They all react with water the same way. If you were going to write the reaction, it looks something like this. And I haven't balanced that. So there, now it's balanced. And all of these things do a reaction that looks pretty much the same way. They make H2 gas. So you can tell they're chemically related because they're all doing this pretty strange reaction. But the properties vary a little bit. Lithium will just make little bubbles of hydrogen gas when you throw it into water. Sodium will make bubbles of hydrogen gas, but it will generate a lot of energy, enough that it's going to ignite some of the hydrogen, and it'll sputter. A chunk of sodium will sputter around on the surface of the water on little jets of flaming hydrogen. And if you throw potassium into water, it will make hydrogen, but also so much heat that it will explode. I mean, it will detonate all of the hydrogen here. This hydrogen will go and react with oxygen there. You'll get this enormous flare of violet fire, if you try to do this reaction with potassium. And you would guess that rubidium and cesium are even more violent when they react. Well, in fact, they're so reactive that rubidium will form an oxide coating over it, and that'll protect it from reacting with water. So it's a little disappointing. You expect it to be even more violent than potassium, and it's not. It's more reactive, but it forms that protective oxide coating. Same thing with cesium. So these things get more and more reactive as you go down the column. So things in the same group are chemically similar. They undergo the same reactions, but they're not all identical. They get more and more reactive. We'd like to be able to explain this, and we've learned to write down electron configurations, and these are going to be extremely valuable in explaining this kind of behavior that we're seeing on the periodic table.